Module 5, Lecture B, Imputation Targets. By the end of this lecture, you will be able to apply univariate, multivariate, and neighbor-based imputation to incomplete data, use missingness indicators, and understand estimators with native missing value support, and transform classification and regression targets using Scikit-Learn target utilities. Imputation methods. Basic value imputation. Basic value imputation handles missing data by replacing each missing entry with a fixed substitute. Numeric values are often filled with the mean, median, or a meaningful constant, while categorical values may use the most common category or an unknown label. This method is simple, fast, and useful for machine learning models that require complete data. Choose missing value replacements based on the variable type and distribution. For numerical data, use the mean when values are fairly symmetric and free of outliers, but use the median when the data is skewed. For categorical data, the most common category can work, though it may overstate that category. If missingness itself may carry meaning, it can be better to create a separate missing category. Basic value imputation can be useful for quick analysis or small amounts of missing data, but it should not be treated as a default solution. Replacing missing values with one number or category reduces variability and can make the data seem more certain than it actually is. When many values are missing, it may distort patterns, correlations, category frequencies, and model behavior, especially if the missingness is not random. For larger data gaps, compare it with more nuanced imputation methods. Python code. Basic value imputation. Simple imputation fills missing feature values with a basic replacement, such as the mean, median, or most frequent value from the available data. Comparing these options shows how each strategy can change the completed dataset. A simple imputer applies the chosen strategy to a small table by replacing each missing entry with the appropriate calculated value. The script imports key tools for data preparation: NumPy for numerical work, pandas for data frames, and Scikit-Learn's simple imputer for filling missing values. It also imports Scikit-Learn itself, so the script can check the library version later. We create a small pandas data frame with age, income, and color data to demonstrate missing value handling. The age and income fields are numeric and include missing entries, while the color field is categorical and also has missing values. This example shows how missing data can appear in both numeric and categorical columns. Before changing the data, the code verifies that the data frame has the expected size, 5 rows and 3 columns. If it does not, it raises an error to warn that the structure is unexpected. This check helps protect data integrity and prevents problems during imputation. Missing values can be handled with different imputation strategies based on the type of feature. For age, the median is used because it is less affected by outliers. For income, the mean is used when values are assumed to be roughly normally distributed. For color, the most frequent value is used because it is categorical data. We first copy the dataset so the original stays unchanged while missing values are filled. Then separate imputers replace missing ages with the median age, missing incomes with the average income, and missing colors with the most common color. After this process, the dataset has no missing entries, and each replacement is based on the chosen strategy for that column. The code simplifies the data by rounding age values to one decimal place and income values to whole numbers. It then converts the rounded income values to integers, making financial data easier to read and interpret. The code checks the Scikit-Learn version to support reproducibility, then reports how many missing values were in the original dataset. It compares this with the number of missing values after imputation to show whether the gaps were filled. Finally, it displays the completed dataset without row indices for a cleaner view. This script shows how to fill missing values in a small dataset using Scikit-Learn's simple imputer. It uses the median for age, the mean for income, and the most common value for color, matching each strategy to the data type. Afterward, it rounds the numeric results and reports missing value counts before and after imputation, confirming that the final dataset has no gaps. Iterative imputation. Iterative imputation fills in missing data by predicting each incomplete feature from the other features in the dataset. Unlike simple averages or most common values, it uses relationships between variables to make more informed estimates. This works especially well when features are correlated, because it captures patterns across the dataset rather than treating each column separately. Iterative imputation fills missing data by repeatedly updating estimates across incomplete features. It starts with rough guesses, then treats each feature with missing values as a target predicted from the others. Repeating this cycle improves consistency, especially when several columns have missing data. Iterative imputation is flexible because you can choose predictive models that fit your data, from simple linear models to more complex tree-based methods. However, it requires careful judgment, can be computationally demanding, and depends on meaningful relationships in the data. The filled-in values are only estimates, so this approach works best when missing data is moderate and preserving relationships is important for later analysis. Python code. Iterative imputation. This demonstration shows how iterative imputation fills missing values in correlated numeric features. Instead of leaving rough gaps, the method predicts each missing value from the other available columns, producing model-based estimates that can be compared with the original missing patterns. We set up the main Python tools for data work by importing NumPy, pandas, and Scikit-Learn. We also enable Scikit-Learn's experimental iterative imputation feature, which lets us use the iterative imputer to fill missing values by predicting them from the available data. We import Scikit-Learn's iterative imputer to fill missing values by predicting each incomplete feature from the others. We also use Bayesian Ridge regression as the imputer's estimator, giving a probabilistic way to model feature relationships and estimate the missing data. A small reproducible dataset is created to model correlated educational features. A fixed random seed ensures the same results each time. Then 12 study hour values are generated from a normal distribution. Attendance is calculated from those study hours plus random noise, making it naturally correlated with study time and similar to a simple real-world education dataset. Grades are modeled using study hours and attendance. The calculation starts with a base grade of 40, then adds twice the study hours and 1/4 of the attendance. A small amount of normally distributed random noise is added to make the grades less predictable and more like real-world data. We use pandas to create a data frame that organizes the data into a table with 3 features: study hours, attendance, and prior grade. Study hours and attendance come from earlier random processes, while prior grade is calculated from those features. This structure makes the data easier to analyze and prepare for handling missing values. We first make a copy of the original dataset so the source data stays unchanged. Then we deliberately add a few missing values in the study hours and attendance columns. This creates an incomplete dataset that can be used to demonstrate how imputation fills in missing information. Before running the imputer, the code verifies that the data table has the expected size, 12 rows and 3 columns. If it does not, it raises an error to signal the mismatch. This check helps ensure the teaching dataset is correctly structured before imputation begins. An iterative imputer is used to fill missing values by repeatedly predicting incomplete columns from the available data. It uses Bayesian Ridge regression, starts with column means, and refines the estimates for up to 10 iterations. A fixed random state makes the results reproducible. And the final output is a complete dataset with missing values filled based on learned patterns. After imputation, the filled array is converted back into a data frame using the original column names to keep the data organized and readable. We then mark where values were missing in the original dataset, so we can later compare those cells and see exactly what the imputation filled in. The code first displays the Scikit-Learn version to confirm the software context and compatibility. It then announces that the next output will show which missing cells were filled by the iterative encoder, helping the user understand how the missing data was handled. The process identifies each missing entry by its row and column position, then uses the column index to find the original column name. It retrieves the corresponding imputed value from the filled data and reports the row, column label, and value rounded to 2 decimal places. This gives a concise view of how the iterative imputer filled the missing values. This script shows how iterative imputation in Scikit-Learn can fill missing values in a small dataset with related features such as study hours, attendance, and prior grades. A Bayesian Ridge model estimates each missing value by using patterns across the other features. The result demonstrates that model-based imputation can provide more informed estimates than simply replacing missing values with the mean or median. Nearest neighbor imputation. Nearest neighbor imputation fills in missing values by comparing an incomplete record with similar records and using their information as the estimate. Unlike a simple average, it uses the pattern of observed features to make a more context-aware guess. The key idea is that similar cases often have similar missing values, so nearby comparable records can provide better estimates than the whole dataset. Nearest neighbor imputation fills missing values by comparing a case with similar cases across multiple variables without requiring a separate statistical model. It is useful for complex or nonlinear data and can handle both numeric and categorical features. Its accuracy depends on choosing a good similarity measure, including adjusting for different numeric scales and representing categories in a meaningful way. Nearest neighbor imputation depends on choosing a meaningful measure of similarity and having enough complete relevant data for comparison. When many values are missing, neighbors may be hard to identify, making the results less reliable. Using one neighbor can preserve local detail but may be noisy, while using several can improve stability but smooth over differences. Treat imputed values as plausible estimates for analysis, not as the true data, and evaluate their impact on model performance and interpretability. Python code. Nearest neighbor imputation. This demonstration shows how nearest neighbor imputation fills missing numeric values in a small table. It uses similar rows to estimate each missing entry, then compares the original and imputed values to show the result. We import NumPy and pandas to work with numerical data and data frames, then use Scikit-Learn for machine learning tools. The nearest neighbor's imputer fills in missing values based on similar records, while the StandardScaler puts features on a common scale. This scaling helps prevent any one feature from dominating the distance calculations used during imputation. We create a small housing dataset with pandas to demonstrate missing data imputation. It includes square footage, bedrooms, bathrooms, and price in thousands, with some bathroom values missing. This simple example shows how similar rows can help fill in missing information. Before transforming the housing data, the code verifies that it has the expected size, 6 rows and 4 columns. If the dimensions are different, it raises an error to stop the process. This check helps prevent problems during later scaling and imputation steps. We use a StandardScaler, so features like square footage do not dominate distance calculations. It centers each feature around its mean and scales it to unit variance, putting the housing data on comparable scales for later analysis. We create a k-nearest neighbors imputer that uses the two most similar rows to estimate missing values. It is then applied to the scaled dataset, filling gaps based on nearby rows and returning a new array with the completed values. The code converts the imputed scaled values back to their original units using the scalar's inverse transform. This restores the data after scaling was used to keep features from dominating distance calculations. The restored values are then placed into a pandas data frame with the original column names, making the imputed housing data easy to compare and analyze. We first find the rows where bathroom values are missing, then create a focused comparison using those rows. For each one, we include the home size and number of bedrooms, along with the missing original bathroom value and the value filled in by nearest neighbor imputation. Rounding the imputed values makes them easier to read and helps show how the imputation changed the dataset. The code first reports the Scikit-Learn version to confirm compatibility. It then notes that missing bathroom values were filled using nearest neighbor's imputation, and displays a clean comparison of the original and imputed rows so the results can be checked easily. This script shows how nearest neighbor imputation can fill missing bathroom values in a small housing dataset. It scales the data first, so square footage does not overpower the distance calculation, then uses the two most similar rows to estimate the missing values, and converts the results back to the original units. Finally, it compares the missing entries with their imputed bathroom estimates, showing how similar homes can support reasonable numeric predictions. Missingness signals. Missingness indicators. A missingness indicator is a feature that records whether a value was originally missing before imputation. This matters because the fact that data is missing can itself be informative, such as a skipped medical test or undisclosed income in banking. Adding this indicator helps a model distinguish between records that receive the same imputed value but had different original data conditions. Missingness indicators help when the fact that data is missing carries useful information for prediction. For example, missing size preferences in retail or missing test scores in education may reflect patterns tied to outcomes. Adding indicators lets a model distinguish real values from imputed placeholders, which can improve accuracy when missingness is systematic. Missingness indicators can help a model use patterns in absent data, but they should be added carefully because they increase complexity and may add noise. They can reflect real, stable signals, but they may also capture quirks of data collection, such as different systems or survey versions, that may not hold in new settings. To use them well, compare models with and without the indicators, check that the patterns are plausible and stable, and consider whether they could unintentionally reveal sensitive information. Python code missingness indicators. This example shows how to keep track of missing data during imputation. Indicator features mark which values were originally missing, and the output compares the data before and after preprocessing. The script imports key tools for preparing data, NumPy and pandas for numerical work and data frames, and Scikit-Learn utilities for handling missing values, building processing pipelines, and standardizing features. It also imports Scikit-Learn itself, so the script can check the library version later. We create a small pandas data table with income and age values to make missing data easy to spot. Some entries are intentionally left missing using NumPy's missing value marker. This simple setup helps illustrate where data is incomplete before handling or filling in those missing values. We use Scikit-Learn's simple encoder to replace missing values with each column's median. It also creates extra columns that mark where values were originally missing. Applying the imputer with fit transform returns a combined array containing the filled data and these missingness indicators. We create a list to store the names of indicator columns for missing values. The imputer identifies which original columns contained missing data, and for each one, we add a new label based on the column name with a was_missing suffix. These labels help track which values were originally missing and later imputed. We build a new table from the imputed data by combining the original column names with the added indicator column names. The result includes the filled values along with flags showing which entries were originally missing. A Scikit-Learn pipeline is created to prepare the data in one step. It fills missing values using the median, adds indicators for where values were missing, and then standardizes the features. Applying the pipeline with the fit_transform method produces a scaled array that is ready for analysis or modeling. The code verifies that the filled data has the expected shape of 5 rows and 4 columns. If not, it raises an error to signal that the imputation and missingness indicator steps did not produce the correct number of columns. The output first shows the Scikit-Learn version to support reproducibility, then displays the original dataset with rounded values so missing entries are easy to see. It then shows the data after median imputation, where missing values are filled and indicator columns mark where they occurred. Finally, it reports the shape of the fully processed data after imputation and scaling, confirming that the pipeline produced the expected dimensions. This script shows how to handle missing values in a small dataset with Scikit-Learn. It fills missing income and age values using each column's median, adds indicators showing where data was originally missing, and then applies a preprocessing pipeline with imputation and standard scaling. It also verifies the imputed data has the expected size and prints the key outputs, including the original data, the completed data with indicators, the scaled result shape, and the Scikit-Learn version. Empty feature handling. Empty features are variables with no observed values during data preparation, often appearing after splitting data or isolating subsets. This can happen when a measurement or category is absent in one sample, but may appear in future data. The main issue is that imputation needs observed values to estimate replacements, so a completely empty feature provides no basis for calculating a mean or pattern. When a feature is empty, decide whether to keep it, remove it, or transform it based on its importance and why the values are missing. Dropping it automatically can cause problems if future data includes that feature, while keeping it unchanged may make models unstable. A common option is to fill categorical features with a placeholder such as unknown, or numerical features with a constant value, but these choices should be made carefully with downstream effects in mind. Empty features can still carry useful information because missing data may reflect how the data was collected, not just a lack of values. A missingness indicator can mark that data was unavailable, such as when a sensor fails or a workflow leaves certain fields blank. These indicators should be used carefully because they can affect fairness and interpretation, so pre-processing choices should be documented and tested. Python code. Empty feature handling. This section explains how imputation handles features that are entirely missing. It compares removing all missing columns with keeping them, and shows that missingness indicators can preserve useful information about where values were absent. We begin by importing key Python libraries for data work: NumPy for numerical operations, pandas for data frames, and Scikit-Learn for machine learning tools. We also use Scikit-Learn's simple imputer to fill in missing values, preparing the data for analysis even when some entries are incomplete. We create a pandas data frame to represent training data with 3 features: age, lab score, and income. Some values are missing, and the lab score feature is completely empty. This example shows how to handle missing data, especially when an entire feature has no available values. A new pandas data frame is created to represent future data with some missing values filled in and others still absent. It includes age, lab score, and income, with a mix of observed and missing entries. This lets us test how the imputation process handles new data, where previously empty features may now contain values. A simple imputer from Scikit-Learn can fill missing values using each column's mean. It is first fitted on the training data, where fully missing columns are removed because no mean can be computed. The fitted imputer then fills missing values in the training data and applies the same rules to new data for consistent preprocessing. A simple imputer is used to handle missing data by replacing missing values with -1. It also records which values were originally missing and keeps completely empty features so the dataset structure stays consistent. First, the imputer is fitted to the training data so it can replace missing values with a constant while keeping the feature structure unchanged. The same imputer is then used on new data to handle missing values consistently. After transformation, the feature names are retrieved, including any missing value indicators, so the original missingness can still be tracked. Before showing the results, the code verifies that the default imputer produces fewer columns than the imputer that keeps empty features. If it does not, it raises an error. This check confirms the expected difference between the two imputers before the lesson continues. The output compares how different Scikit-Learn imputers handle missing data. It first checks the Scikit-Learn version and the original number of training columns, then shows that the default imputer may drop columns that are entirely missing. In contrast, the imputer that keeps empty features retains those columns and adds missing value indicators. The final transformed row shows how missing values were filled and how the indicators were added. This script compares two ways to handle missing data. A default imputer fills missing values with the mean, but removes columns that are completely empty, which can reduce the number of columns after transformation. A second imputer keeps all columns by filling fully missing ones with a constant value and adding missingness indicators, preserving the original data structure. The example shows why the imputation strategy should match the expected schema, especially when future data may contain values in columns that were previously empty. Native missing support. Native missing support lets some models learn directly from missing values instead of requiring them to be filled in first. This matters because the fact that data is missing can itself carry useful information, especially when the missingness is related to the outcome or other features. By treating missing entries as part of the learning process, these models can avoid artificial patterns that may come from replacing gaps with averages or other stand-ins. Tree-based models handle missing data well because they can learn separate decision paths for missing and observed values. During training, decision trees and gradient-boosted trees choose where missing records should go to improve predictions. This lets the model use missingness as useful information, such as when a missing property age or product rating may signal something meaningful. Native support for missing values can simplify modeling, but it still requires careful validation. Analysts should know which models handle missing data, how they work with different data types, and whether alternatives, like imputation with indicators, perform better. The best approach depends on the dataset and why values are missing, so missingness should be treated as part of the modeling process rather than ignored. Python code, native missing support. This example compares models that handle missing values directly. It highlights that missing data can contain useful predictive information, and the reported scores show how two modeling choices perform. We import NumPy for numerical work and Scikit-Learn tools for building and evaluating machine learning models. The key components include a gradient boosting classifier that can handle missing values, an imputer for filling missing data, and logistic regression, which requires complete data. We also use accuracy scoring to measure performance, train test splitting for fair evaluation, and a pipeline tool to combine preprocessing and modeling into one workflow. We create a small, reproducible dataset where missing values can carry information. A fixed random seed is used, then 300 values are drawn from a normal distribution to form the feature data and mimic real-world variability. A random set of 300 feature values is created, and some entries are marked as missing based on a fixed probability. The binary target is then defined using both the feature value and whether that value is marked missing. This makes the target partly depend on missingness, so the setup can test how well models handle missing data. We first copy the feature data so the original stays unchanged. Then, wherever the missing data signal is true, we replace the copied values with NaN, NumPy's marker for missing values. This creates a realistic dataset with missing entries, which can be used to test how models handle incomplete data. The code prepares the data for modeling by reshaping the feature values with missing data into the two-dimensional format required by Scikit-Learn. It also stores the target values as the labels the model will learn to predict. Together, these steps put the features and targets in the right form for the next modeling stage. The code first counts missing entries in the feature matrix by checking for not a number values and summing them. It then verifies that at least one missing value exists. If none are found, it raises an error because the later modeling step is meant to demonstrate how missing data is handled. The dataset is divided into training and testing sets, so the models can be evaluated fairly. Using Scikit-Learn's train test split function, 30% of the data is held out for testing, with a fixed random state for reproducibility. Stratifying by the target variable keeps the class proportions consistent in both sets. A pipeline combines preprocessing and modeling into one workflow. Here, missing values are first filled using a simple imputer that replaces them with the mean of the available data. The imputed data is then used to train a logistic regression model, with settings chosen to support convergence and reproducible results. We use Scikit-Learn's Histogram Gradient Boosting classifier to build a tree-based model that can handle missing values without extra preprocessing. The model runs for 60 boosting rounds with a learning rate of 0.08, which controls how strongly each round updates the model. A random state of 42 makes the results reproducible each time the code is run. Two models are trained on the same training data for a fair comparison. The logistic regression model first fills missing values with the feature mean, then learns the relationship between the features and the target. The histogram-based gradient boosting classifier is also trained on the same split, but it can handle missing values directly and may use that missingness as useful information. We compare two ways of handling missing data by measuring each model's accuracy on the test set. One model uses mean imputation before logistic regression, while the other is a tree-based model that handles missing values directly. By comparing their predictions with the true test labels, we can see which approach performs better. The output first checks the Scikit-Learn version and reports how many feature values are missing, setting context for the comparison. It then compares accuracy from mean imputation followed by logistic regression, with a tree-based model that handles missing values directly. The key takeaway is that native missing value support can use missingness as useful information without filling values in advance. This example compares two models on data where missing values help predict the target. Logistic regression must first replace missing values with the mean, while a histogram-based gradient boosting classifier can use missing values directly. After training and testing both models, their accuracy scores show how native missing value support can improve performance by learning from the missingness itself. Target transformations. Encoding class labels. In classification tasks, class labels often need to be converted into numbers so machine learning models can use them. Scikit-Learn provides a way to encode each target label as an integer, while preserving which class it represents. This is applied to the target values, not the input features, and is useful when labels come from readable text. The encoded labels let the model distinguish classes, and predictions can later be converted back to the original label names. When class labels are encoded as numbers, those numbers should be treated only as category identifiers, not as measurements or rankings. Even labels that seem ordered, such as low, medium, and high risk, are used by the classifier simply to mark class membership. After prediction, the numeric labels can be converted back to their original names, such as spam or deer, to make the results easier to understand. Class label encoding must stay consistent from training through deployment, because changing the mapping can make predictions or reports mean the wrong thing. Scikit-Learn helps by storing the link between original labels and encoded values, so results can be translated back correctly. If new labels appear after training, it may signal that the model or data collection process needs to be reviewed. Python code. Encoding class labels. Use a label encoder to convert text class labels into numeric targets for classification. It keeps the class mapping, so model predictions can be converted back into readable labels. We import key tools from Scikit-Learn for a classification task. The label encoder converts categorical labels into numbers, so machine learning algorithms can use them, while the decision tree classifier builds a model that predicts discrete outcomes based on data features. Credit scores and incomes are stored as two related feature lists for customer applications. A pairing function combines each score with its matching income, creating one feature pair per customer. This organized structure is suitable for machine learning models because it matches the input format used for training and prediction. Target labels, such as denied and approved, describe the outcomes we want to predict, but machine learning models need them as numbers. A label encoder from Scikit-Learn converts these text labels into unique integers. Fitting and transforming the labels produces a numeric version that can be used for model training. We check the Scikit-Learn version to support compatibility and reproducibility. Then review the encoder's stored classes to confirm how text labels were mapped to numbers. Finally, we inspect the encoded target values to verify that the original status labels were converted correctly and consistently for model training. We create a decision tree classifier with a maximum depth of 2 to keep the model simple and reduce overfitting. A fixed random state makes the results reproducible. The classifier is then trained on the input features and encoded status labels, so it can learn patterns for prediction. New customer applications are represented by their credit score and income, then passed to the trained model to predict whether each one should be approved or denied. Because the model returns encoded numeric labels, the encoder's inverse transform method is used to convert them back into readable approval statuses. This makes the model's output understandable for human interpretation. We first view the model's predictions as encoded numbers, which show the raw class outputs for new applications. Then, we convert those numbers back into readable class labels using the label encoder. This makes the results easier to interpret and understand. This example shows how Scikit-Learn converts text class labels, such as approved and denied, into numbers so a decision tree can learn from customer application data like credit scores and income. After training, the model predicts new applications in encoded form, then converts those predictions back into readable labels. The output also shows the Scikit-Learn version, the class order, and both encoded and readable predictions, illustrating how categorical labels can be used in machine learning while keeping results interpretable. Multilabel binarization. Multilabel binarization is used when one observation can have several labels at the same time, rather than just one category. it converts each sample set of labels into binary columns, where each column shows whether a specific label is present. This gives machine learning algorithms a structured numerical format for learning patterns across multiple possible labels. Multilabel binarization treats each label as its own separate output, instead of merging label combinations into many rare classes. This lets a model learn shared patterns for labels such as comedy, while still recognizing other labels like romance or drama. The binarized label order must stay consistent, because each column represents a specific label, and that mapping is needed to interpret predictions correctly. Multilabel binarization converts multiple possible target labels into a numerical format that machine learning models can use. It should be fitted on the expected labels during training and reused on new data so predictions stay consistent and interpretable. This changes only how the targets are represented, not the underlying multilabel problem, so the estimator and evaluation method must still be chosen carefully. Python code, multilabel binarization. This example shows how the multilabel binarizer converts lists of labels into binary target columns. Each possible label becomes its own column, making it easy to encode labels and decode them back again. We import pandas for working with structured data, then use Scikit-Learn's multilabel binarizer to prepare multilabel data. This tool converts lists of labels into binary columns, making the data easier to use in machine learning. The data is set up so each movie can have one or more genre labels, such as comedy, romance, drama, action, documentary, or history. This represents a multilabel classification problem, where a single item may belong to multiple categories. The structure is then ready for multilabel binarization, which converts each genre into a binary feature for further processing. We use Scikit-Learn's multilabel binarizer to convert movie labels into a binary matrix. Its fit transform method learns all unique labels, sets them as columns, and marks each movie with ones for labels it has and zeros for labels it does not have. A pandas data frame is used to make the binary target matrix easier to read. Its columns use the class labels learned by the binarizer, so each row clearly shows which labels apply to a movie. Printing the learned label order helps explain how the columns are arranged before displaying the final binary label representation. The fitted binarizer is used to convert binary target data back into the original label format. Its inverse transform method reverses the binarization, turning the binary matrix into label sets. The result is then printed for the first movie to show which original labels its binary values represent. This script shows how Scikit-Learn's multilabel binarizer converts movie genre lists into a binary matrix for machine learning. It learns the unique genres, assigns each one a column, and marks each movie with ones for genres it has and zeros for genres it does not. The result is displayed in a pandas data frame, then converted back to the original genre labels to confirm the encoding worked. Transformed targets. In regression, targets such as prices or energy use can be skewed, which may make models overreact to extreme values and produce unstable predictions. Target transformation addresses this by training the model on an adjusted version of the target, then converting predictions back to the original scale. In Scikit-Learn, this can be done by wrapping a regression model so results remain accurate and interpretable in familiar units. A logarithmic transformation can make skewed targets, such as house prices, easier for a model to learn by emphasizing proportional differences rather than raw size differences. This is helpful when relative error matters more than absolute error. After prediction, the results are transformed back to the original scale, so they remain easy to interpret in real-world terms. Target transformations can improve model performance by making the feature-target relationship easier to learn, but they also change what the model is trained to predict. They must be used carefully, especially when targets include 0 or negative values, or when the inverse transformation may introduce bias. Always evaluate results on the original scale with metrics that match the real-world goal, and use Scikit-Learn tools to handle these transformations consistently. Python code. Transformed targets. This example handles a skewed regression target by training the model on log-transformed prices. After prediction, the results are converted back into the original dollar units. We import the main tools needed for a regression workflow: NumPy for numerical work, Scikit-Learn for machine learning, and utilities for splitting data, training a linear regression model, transforming the target variable, and evaluating predictions with mean absolute error. Together, these imports support training the model and testing its performance on unseen data. We set up NumPy's random number generator with a fixed seed of 42, so the synthetic data is reproducible. This means each run produces the same random sequence, which helps keep experiments consistent and makes debugging easier. This process creates a simulated housing dataset with 300 samples. Home sizes are randomly generated between 600 and 3200. Then random noise is added to introduce variability. Prices are calculated by applying an exponential transformation to a linear combination of the home size, a constant, and the noise. The result is a positively skewed price distribution, reflecting the idea that larger homes tend to have much higher prices. To prepare the data for regression, the home size values are reshaped into a two-dimensional feature matrix, as required by Scikit-Learn. The price values are then set as the target the model will learn to predict. Together, these inputs prepare the data for training and testing the regression model. Before using a logarithm transformation on the target values, the code verifies that every value is positive. This matters because logarithms are not defined for 0 or negative numbers in real numbers. If any non-positive value is found, the code raises an error to prevent an invalid transformation. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. A quarter of the data is kept for testing, so the model can be evaluated on data it has not seen before. Setting the random state to 42 makes the split reproducible, which helps ensure consistent performance results. We create a linear regression model with Scikit-Learn and train it on home sizes paired with their prices. The model learns the relationship between size and price, then uses that pattern to predict prices from new home sizes in the test data. The predicted values are in dollars, matching the original price targets. A transformed target regressor is used to wrap a linear regression model and apply a log-based transformation to the target values during training. This can make skewed targets easier to model. After fitting on the training data, the model automatically converts predictions back to the original scale using the inverse transformation when predicting on the test data. We compare two models using mean absolute error, which shows the average size of prediction errors in the original dollar values. First, we measure the plain model, then the model trained with a logarithmic target transformation and converted back for prediction. Comparing these errors tells us whether transforming the target improves accuracy. The output first reports the Scikit-Learn version to support reproducibility. It then compares mean absolute error for a standard linear model trained on dollar prices with a model trained using log-transformed target values. This shows whether transforming the target improves prediction accuracy. Finally, it gives a sample prediction from the transformed model converted back into dollars, so the result is in the original scale. This script shows how transforming a skewed regression target can improve a model. It creates synthetic home size and price data, trains a standard linear regression model, and compares it with a model that learns from log-transformed prices before converting predictions back to dollars. The transformed target approach usually produces a lower mean absolute error, showing better performance on skewed price data. The output includes the Scikit-Learn version, both error scores, and an example prediction in dollar units. In this lecture, you learned to apply univariate, multivariate, and neighbor-based imputation to incomplete data, use missingness indicators, and understand estimators with native missing value support, and transform classification and regression targets using Scikit-Learn target utilities. In the next module, Module 6, we will go over composite estimators.
Thank you for your attention. See you all in the next lecture.